the bracket A, that can be expressed as alpha in bracket beta into A. Okay, and similarly we can write here that in bracket alpha beta into B outside the bracket B, that can be expressed as alpha in bracket beta into B. So that property we already have in for real numbers. So alpha now next one is from this step to this step we have to use the definition of scalar multiplication, that is alpha beta A 1 1 beta B. And now what is this one? This is exactly beta A, so alpha in bracket beta A. And similarly we can prove that in bracket alpha beta A, that is equal to beta in bracket alpha A. Okay, so it's quite easy to prove. Now in the last property, 1 be the unit element of R, then for every A 1 into A, that is equal to 1 A1 1B, that is equal to 1 into A 1 1 as it is 1B, so that is equal to A1 1B, that is equal to A. So 1 into A, that is equal to A, that we prove, and thus all the 8 exams are satisfied for the given set 2 cross 2 matrices, as the given set is a vector space. So we prove all the 10 conditions here, 8 conditions, and another 2 conditions are automatically satisfied because it's already defined in the statement of the example, addition, closeness, and for addition and scalar multiplication. So all the 10 conditions are satisfied for this example. So we can see that the given set is a vector space, okay, under the given addition and scalar multiplication which is given in the example. So this question was complete. Next question. Question 4b. Which of the following are subspace of R3? First one is all the vectors of the form ABC where B is equal to A plus C. So this second coordinate is basically the addition of first and third coordinate. Okay, so only those type of elements are in the set. And next one is all the vectors of the form ABC where B is equal to A plus C plus 1. In this set, the second coordinate is not just addition of first and third coordinate. The second coordinate, that is equal to the addition of first coordinate plus last coordinate plus 1. Okay, so let's try to check that the given set is a subspace or not. Now first of all, try to understand what is the definition of subspace. If W is a subset of a vector space V, right? If W is a subset of a vector space V, and we need to prove that W is a subspace of a vector space V. What we have to prove? We have to check only the 2 conditions. The first one is UV. For any UV belongs to W, we have to prove that U plus V belongs to W, and for any alpha which is a scalar, alpha belongs to R and U belongs to V, U belongs to W, we have to prove that alpha into U, that is also belongs to W. So if these 2 conditions are satisfied, right, closeness for addition and scalar multiplication for W, then we can say that W is a subspace of a vector space V. Okay, W is a subspace of a vector space V. Instead of W here we use V. Okay, so that U is equal to A1 B1 C1 and V is equal to A2 B2 C2 belongs to V. Now belongs to V means we are first of all checking the first example, okay, where ABC is equal to B, where ABC, all the vectors of the form ABC where B is equal to A plus C. So for the first example, if U and V belongs to V, that means what? This B1 is equal to A1 plus C1 and this B2 is equal to A2 plus C2. Because of these 2 elements are in the set, so definitely it satisfied the condition for the set. So B1 is equal to A1 plus C1 and B2 is equal to A2 plus C2. So U plus V, now try to prove that U plus V belongs to V or not. Now what is U plus V? Using the standard addition, A1 B1 C1 plus A2 B2 C2, that is equal to A1 plus A2 B1 plus B2 C1 plus C2. Now to prove that U plus V, belongs to V, what we have to prove? The second coordinate, that is equal to addition of first and last coordinate. What is our second coordinate? B1 plus B2. What is our second coordinate? B1 plus B2. That is equal to A1 plus A2 plus C1 plus C2. Is it satisfied? You can see B1 plus B2. Put the value of B1. What is B1? B1 is A1 plus C1 and B2 is A2 plus C2. So clearly B1 plus B2 can be expressed that is equal to A1 plus A2 plus C1 plus C2. Okay, so the first condition is satisfied. So V is closed under the addition, vector addition. Now let's try to check the scalar multiplication. Alpha into U, that is equal to alpha into A1 B1 C1, that is equal to alpha A1 alpha B1 alpha C1. Now to prove that this element alpha into U belongs to V, what we have to prove? Again the second coordinate, that is equal to addition of the first and last coordinate. So alpha into B1, that is equal to, put the value of B1 alpha into A1 plus C1. Here you can see B1 is equal to A1 plus C1. Okay, so here we put the value of B1 alpha into A1 plus C1, and alpha into A1 plus C1 can be written as alpha A1 plus alpha C1, and this is exactly the addition of first and last coordinate of the element alpha U. Okay, so alpha B1, that is equal to alpha A1 plus alpha C1. Okay, so again the V is not only a closed under vector addition, but that is also closed under the scalar multiplication. Okay, V is closed under the scalar multiplication. So that's why V is a subspace of R3. Now for 2, that U is equal to B1 A1 B1 C1 and V is equal to A2 B2 C2. Now what is our example 2? You can see all the vectors of the form ABC, where B is equal to A plus C plus 1. That means the second coordinate must be addition of the first coordinate plus plus third coordinate plus 1. Okay, so let U is equal to A1 B1 C1 and V is equal to A2 B2 C2 belongs to V. Now that means what? B1 is equal to A1 plus C1 plus 1 and B2 is equal to A2 plus C2 plus 1. Okay, now U plus V, try to check that U plus V belongs to V or not. So what is U plus V? U plus V is equal to A1 B1 C1 plus A2 B2 C2. So B1 plus B2, that is equal to A1 plus, put the value of B1 and B2, A1 plus C1 plus 1, this is the value of B1, and A2 plus C2 plus 1, that is the value of B2. So that can be expressed as A1 plus A2 plus C1 plus, not equal to, this is not equal to A1 plus A2 plus C1 plus C2, because okay, so that's why V is not closed under vector addition, because this 1 plus 1, that is equal to 2. So we get B1 plus B2, that is equal to A1. What we expect, you can see B1 plus B2, if U plus V belongs to V, that means what? This B1 plus B2, that is equal to A1 plus A2 plus C1 plus C2 plus 1. But what we here get, A1 plus A2 plus C1 plus C2 plus not 1 plus 2. Okay, so that is a contradiction. So that's why V is not closed under the vector addition, and only one condition is dropped, that means V is not a subspace of R3. Okay, so here the solution of this question, and this question was asked in 4 marks in this question paper. Next question, question 4C. Let V1 is equal to 1 minus 3x plus 2x square. Here 3 polynomials V1, V2 and V3. V1, V2 and V3. We have 3 polynomials of P2. 1 minus 3x plus 2x square, that is V1. V2 is 1 minus x plus 4x square. V3 is 1 minus 7x. Show that the set S V1, V2, V3 is a basis for P2. P2 means set of polynomial of 2 degree. Okay, P2 means set of polynomial of 2 degree. So here to prove that this set is a basis for P2, basically we have to need to prove the two conditions, the two properties by definition of basis. Now what is the definition of basis? Just try to understand. B is a basis for a vector space V if The first one is B is linearly independent, and second one is the span of B. Okay, that means the set of all linear combination of the vectors of B, that is equal to the vector space V. Okay, the span of B means the set of all linear combination of the vectors of B, or here S, so whatever it is, B or S or Q, whatever it is, so the span of B, that is equal to V. That means the set of all linear combination of the vectors of the set B, that is equal to vector space V. But if there is a one important theorem which we will use to solve this example, just try to understand very carefully. Because of using this example, using this theorem, we can easily solve this example with short method. Okay, so you can see here is a theorem. Here we use one important theorem, that if dimension of V is equal to n, okay, that you should know that some of the dimension of some of the important vectors, vector space, that you should know that dimension of, in general, dimension of Rn is equal to n, in general dimension of Pn, by set of polynomial of n degree, so the dimension of Pn is equal to n plus 1, dimension of set of m cross n matrix, that is equal to m into n. Okay, so some of the sets, some of the dimension of some of the important sets that you should know. Okay, and using that dimension we can use this theorem, that here we use one important theorem, that if dimension of V is equal to n and S contains exactly n vectors, sorry, this is not a 3 vectors, this is n vectors, then S is a basis for V if S is linearly independent or S spans V. So instead of to check both of the properties, you just only need to prove one property, one conditions. Okay, so that's why here we use that theorem. Same situation happen here. You can see dimension of P2. What is our vector space? P2. What is dimension of P2? P2 is equal to 3, and S contains 3 vectors. You can see S contains 3 vectors, 3 polynomials. Okay, so exactly the same situation happen here. So we only need to prove that S is linearly independent, because it's quite easy to check. To prove linearly independent or to check linearly independent, it's basically easy. Okay, instead of to check the span. So, and here to prove linearly independent, we are checking the determinant, the value of determinant of this 3 polynomial. If the value of determinant that is non-zero, then the set is linearly independent, otherwise it is linearly dependent. That you should know. Okay, so we use this important theorem to solve this example. Okay, and here is a determinant. The first row is coming from the first polynomial, that is 1 minus 3 2. The second row is coming from the second polynomial, that is a coefficient of that is first one is constant, second and third one is the coefficients of x and x square respectively. So 1 minus 1 4. Okay, again the third row is coming from the third polynomial, so 1 minus 7 0, that is equal to 1 into. Now you can know that how to solve this determinant. Okay, 1 into minus 1 into 0 minus 4 into minus 7, so that is 28, then plus 3, this is plus 3 into 0 minus 4. Okay, so this is minus 12, this is actually minus 12. Okay, 28 minus 12, and then plus 2 into minus 7 minus plus 1, so that is minus 6, so that is minus 12. So this is 28 minus 12 minus 12. So again this is actually 4 not equal to 0, but we only need to check that it is 0 or non-zero. So definitely the value of this determinant is 0. So hence S is linearly independent. So S is a basis for R3 using this theorem. Okay, S is linearly independent, so S is a basis for R3. You don't need to check that S spans V or not, that is automatically satisfied. Okay, so here the complete the solution, and this question was asked in 4 marks in this question paper. Next question 5. 5a, use the inner product. How we define inner product fg, where fg is equal to integration from 0 to 1 fx gx dx, and to compute distance from f to g and norm f, where fx is equal to x, gx is equal to e raised to x in continuous function from 0 to 1, closed interval from 0 to 1. Now what is distance from fg? What is the formula for distance of f from f to g? That is exactly norm f minus g. Okay, in inner product space, distance of fg, that is norm of f minus g. Okay, and how we define norm of f minus g? That is exactly the square root of inner product f minus g with f minus g. Okay, again the norm f is square root of inner product f with f. Okay, so here is the formula, that distance of fg, see, distance of fg, that is equal to norm of f minus g, and that is exactly the square root of inner product f minus g with f minus g. Okay, and again norm f square, that is inner product f with f. So norm f is actually square root of inner product f with f. So first of all we have to find the f minus g. Here we have f of x is equal to x and g of x is equal to e raised to x. So what is our f minus g? F minus g, that is equal to x minus e raised to x. Okay, now first of all we find inner product f minus g with f minus g. So that is equal to integration 0 to 1. What is f minus g? Now here is the definition for inner product fg, that is equal to integration 0 to 1 and then multiplication of this two function f and g. Okay, so similarly when we apply this definition for to find inner product f minus g with f minus g, that is equal to integration 0 to 1 f minus g into f minus g, that means f minus g square. Now what is f minus g? X minus e raised to x, so that's why x minus e raised to x square. Okay, dx.